the complete pathway, going all the way from star and planet formation to the changes that occur on young planets that then lead us into more and more complicated forms of life, something I'm sure you'll hear more about. Okay. So, we know a lot more about the chemistry leading to nucleotides, but I don't want to hear metals like iron and nickel, sulfides, and on the surface of these crystals, hydrogen and carbon can get together, and the surface catalyzes the formation of linear chains of carbon atoms with oxygen at the end. And these molecules can get released and float up. And those are exactly the molecules that you need to build these membranes. The very robust chemistry, very simple. And then these can be swept up to the surface and concentrated in various geochemical scenarios.
I want to move on a bit from the origin of life and use my biologist's intuition to try to speculate about whether we can make any educated guesses about what extraterrestrial life might eventually look like once it has originated. Variable focus, variable stopping down, and then the retina at the back with millions of, let's call them pixels, or little. These two groups of fish have certainly evolved independently. One group in the New World in South America, the one on the left, and one group in Africa, the one on the right. Now there's an interesting and revealing difference between these two groups of fish. In order to do electrolocation at all, the fish needs its body to be dead straight.
Can you hear me? Good. That's also a quotation from Richard Dawkins. So I'm going to be talking about black holes, and I would like to begin with an idealized description of how black holes are born. You'll hear a much more realistic description of this from Adam Burrows later on in this meeting. If you have around a black hole, you see there's obviously a very massive object here around which those stars are moving. And that is the evidence for it. And you can weigh the black hole by applying Kepler's laws to the motion of those stars, and that's how you, very interesting, must happen. They must really excite the warping of space and time in some wild sort of a way. And so I would like to understand what happens to warp space-time in this kind of a collision when three tornadoes come crashing together and they're made from whirling space instead of being made from air. We have made some major discoveries about what happens in the last several years, and most of them in the last 9 months. In the numerical relativity community, first really got their codes going really well. It was a process that took nearly a half a century to get numerical relativity up and running successfully. Here we see a simulation by a group at Caltech, Cornell, and the Canadian Institute for Theoretical Astrophysics. You see the two black holes as we would see them in our universe against the dark blue sky up here. You see the warped space and time down here, seen by a bulk being looking in. Here you see the very simple gravitational waveform that's emitted when the black holes are not spinning. We've jumped over to where they're much closer together because the in-spiral was boring. I'll pause the movie while you admire the merger. And then the black holes vibrate and settle down into a final state. The collision here. I have not mastered this. Let me just walk it through. So you see the squeezing tendex at the net, the stretching tendex at the ends. It overshoots, and we've got a squeezing tendex at the ends, and a stretching one at the equator, and it's a plane. We're going to see what happens as the black holes orbit Notice they go down together, then up together, down together, up together, in apparent violation of momentum conservation. Then they get a big kick. And that post that is taking off on is an artifact of the visualization. It shouldn't be there. Okay, so but the main thing is that the black holes get a very large kick, a large enough kick in this case to eject. So here they are. The water around this one is going like that, and it advects that vortex down. The water around this one was going like that, and it advected the other vortex.
In both these cases, the temperature difference was 0.4 degrees globally. That does not mean that locally the temperature was 0.4 degrees different, since different parts of the globe have changed quite differently. Now, is this recent temperature rise extraordinary? So you have to look back in time, and that becomes difficult because, the thermometer hasn't been invented for such a long time. Is the external source of energy for the Earth. So it delivers 1.36 kilowatts per every square meter of ground facing the sun. This is, at noon when the sun is high, if there are no clouds. That means it's fairly common on the south side of Tenerife, very, very common in Germany where I live. The atmosphere has temperatures ranging anywhere between a couple of thousand degrees and 10 million degrees, or even more. So what you see in the lower movie is gas at something like 10,000 degrees, that's a few thousand kilometers